The goal of a communication system is to transmit messages from an information source to its destination in a most efficient manner. An essential step in order to achieve this goal is to represent or transform or map the sequence of source symbols from this source into another sequence consisting of symbols called code symbols from another alphabet called code alphabet. This transformation or representation or mapping from one sequence to another sequence is achieved by what is commonly known as source coder. The task of a source coder is to represent messages as compactly as possible. Therefore, the efficiency of a source coder can be judged by the compactness of the messages it achieves, and this can be measured in a way by the average code word length of the code which it generates. Now, the question that arises is, how do I synthesize such codes? Let us take a simple example. If I have a source S consisting of source symbols, then messages will be generated consisting of the source symbol from this source alphabet S. These messages which are being generated from this source are to be compactly represented by a source coder. As we have said, that the efficiency of the source coder will be decided by the compactness of the messages, and this can be measured in terms of the average word length or average code word length. We will look into the definition of all this term as we progress today. Now, the question that arises is, the first question that arises is, what is the minimum achievable average code word length for a given source? The second question that arises is, how does one design a source coder which achieves this minimum length? Now, we will see that minimum achievable average code word length for a source S will be related to the entropy of the source S, and it is very difficult to design a source coder which achieves this minimum length. It may not be possible for us to design an optimum source coder for all the types of sources. Only when source satisfy some particular constraint, then we will see that it is possible for us to design an optimum source coder. So, for those sources when it is not possible to achieve the optimum source code design, then in that case we should look for the strategies to develop or design source coders which come very close to this minimum length. So, practical designs of source coders which are very close to the optimum source coder. Based on the definition of information measures and entropy calculation for the sources, we will try to answer these three questions. So, let us look little more into depth into the connection between the source coding and the information theory concepts which we have studied so far. In order to do that, let us define formally what is a code. So, definition of code will be given as, let us consider a set of symbols comprising a given alphabet, and that alphabet is called as S. This alphabet S consists of Q symbols or Q letters. Then we define a code as a mapping or transformation or representation of all possible sequences of symbols of source alphabet S into sequences of symbols of some other alphabet X. This alphabet X consists of R symbols or R letters, and these symbols or letters of this alphabet X are known as code letters or code symbols. We call S the source alphabet and X the code alphabet. So, in short, code is nothing but a mapping from a sequence of source symbols to a sequence of code symbols. Now, this definition of code is too general to be of much use in code synthesis. So, what it implies that we should try to put some more restrictions on the definition of code. The first properties which we require for a code to satisfy is what is known as a block code. So, let us look at a definition of a block code. A block code by definition is a code which maps each of the symbols of the source alphabet denoted by S into a fixed sequence of the code symbols from the code alphabet X. This fixed sequences of the code alphabets X, that is sequences of Xj, are called code words. Each code word corresponding to a particular symbol in the source alphabet would be denoted by Xi. So, Xi is the code word corresponding to the symbol Si in the source alphabet. Let us look one example to understand this definition. So, an example of a block code. Let me assume that I have a source alphabet consisting of 4 source symbols denoted by S1, S2, S3 and S4. I have my code alphabet X consisting of code letters or code symbols which are 0 and 1. So, this would be an example of a binary block code because the code alphabet consists of only 2 elements or 2 letters or 2 code symbols which are 0 and 1. So, let us design one code for this. Designing of a code for this source would be trying to find out the code words for each of these source symbols. So, the code words which are denoted by Xi would be, for S1 let me have 0, for S2 let me have 1 1, for S3 let me have 0 0, and for S4 let me have 1 1 again. So, this are the code words corresponding to the source symbols. This is the code word for the source symbol S1, this is the code word for S2, and similarly this is the code word for the source symbol S4. This would be an example of a binary block code. At a first glance, the requirement that we encode the source symbols one at a time into fixed sequences of code symbols seems quite severe. Note, however, that if a code maps all sequences of source symbols of length n, that is small n, into a fixed sequences of code symbols, then the code maps each and every symbol from the nth extension of the source S, original source S, into a fixed sequence of code symbols with code alphabet Sn. This property we will see very shortly. In the light of this property, we will realize that this definition of a block code is not that severe. A set of rules transforming a source alphabet into a code alphabet will satisfy our definition of block code only when we consider the symbols from the nth extension of the source S. Now, if you look at this code which I have designed, this would be this I will call as a code. This is a particular code for this source S, and this code has been formed based on this code alphabet 0 and 1, and these are the code words. Now let us, if you want to really use this code in a practical situation, there is some problem. The problem is that if you look at the code words for the source symbol S2 and S4, they are identical. So even if I consider messages of length 1, that means messages consisting of source symbols of length 1, and when I receive the code symbols 1 1, there will be ambiguity for me to decode the value of the source symbol. 1 1 could correspond either to S2 or it could correspond to S4. What this example implies that we should put further restrictions on block codes. The first natural restriction which we should put for a block code is that all the code words which we form for a code should be distinct. So a block code should be formed in such a way that all the code words in that code are distinct, and such a block code is known as a non-singular block code. So let us formally define a non-singular block code. So definition of a non-singular block code would be: a block code is said to be non-singular if all the code words of the code are distinct. An example of such a non-singular block code would be let me again consider source symbols S1, S2, S3, S4. Corresponding to the source symbol, let us assume that the code words are 0, 1 1, 0 0, 0 1. Now this code satisfies the definition for non-singularity of a code, because all the code words out here are distinct. But again there is some problem with the design of this code. Take a simple example. If I were to receive a sequence 0 0 1 1, then when I receive this sequence, I can decode this sequence as S3, S2, or I could decode this sequence as S1 followed by S1 or followed by S2. So on the receipt of the sequence, the code symbol 0 0 1 1, there is an ambiguity about the transmission of the source symbols. So though this code was non-singular in the sense when I considered the source symbols as individual entity, but when I consider the transmission of source symbols in block, then there is an ambiguity in the decoding. So it means that we should put further restrictions on non-singular block codes in order to arrive at the codes which are more useful. Now, in order to do that, let us try to define what is known as an nth extension of a block code. We had defined an nth extension of a source S. So, let us try to define in a similar manner an nth extension of a block code. So, in order to do that, let us consider I have a block code which maps all the source symbols from the source alphabet S into a fixed sequence of code symbols from a code alphabet X. Now, this source itself S could be nth extension of some other source. It is not of importance to us. Since we are restricting our discussion to block codes, then we have a natural elementary unit, namely for each symbol in S, we have fixed sequence of code symbols given by a particular code Xi. This forms one unit. Now, putting these building blocks together, just as we did for nth extension, where the successive symbols from an elementary source were put together to define an nth extension of a source S. So, similarly we can define the nth extension of a block code based on this elementary unit. Let us try to define an nth extension of a source, of a block code. So, the nth extension of a block code which maps the symbols Si into the code words Xi is the block code which maps the sequences of source symbols Si1, Si2 up to Sin into the sequences of code words Xi1, Xi2, Xin. Xi1 is the code word corresponding to the symbol Si1. Similarly, Xi2 is the corresponding code word for Si2, and finally Xin is the corresponding code word for the symbol Sin. So, you form the sequences of source symbol of length n, then to get the sequences of code symbols for this sequence is just concate the code words, the corresponding code words, and that is how we form the sequence of the code symbols for this. Now, by definition, the nth extension of a block code is also a block code. Let us try to understand this concept with the help of a simple example. Let us again consider the block code which we had designed earlier. This is a block code, binary non-singular block code which we had talked of. So, I have 4 symbols and I have 4 distinct code words for it. So, this is an example of non-singular block code. Now, the second extension of this would be the second extension of the source S1, S2, S3, S4 will comprise of 16 symbols. So, the second extension of the source S2 will comprise of 16 symbols which have been given here, listed here. Now, to form the code words corresponding to this 16 symbol is very easy. Look at the code words for each symbol and concat them. For example, if you take S1, S1, the code word corresponding for S1 is 0. So, the code word corresponding to S1, S1 is 0, 0. Similarly, S1, S2 would be 0, 1, 1. S1, S3 would be 0, 0, 0. S1, S4 concatations of the code words, respective code words, give us the code word for the extension. So, S3 is 0, 0, S1 is 1, S3 is 0, 0, 1, 1. So, this is the code which I generate for the second extension. Now, if you look at this code which we have generated for the second extension by the definition of any extension of a block code, we will find that this second extension, this code which we have generated is not a singular, it is not non-singular, because if you look at S1, S3 and S3, S1, the code words for both this are identical. Now, if the code words are identical for this source symbols, then by definition this is not non-singular. Similarly, if you take the third extension of this source, you will have 64 combinations, and one of the combination you will get S1, S1, S3, and for that the code word will turn out to be 0, 0, 0, 0, and for S1, S3, S1 it will turn out to be 0, 0, 0, 0. So, again you will find that this is one example. There could be many more like this when you try to do the third extension of the block code. Now, in this, if you look for this case, you will find that both the code words are same for two symbols in the third extension of my preliminary source given earlier. So, what it means that if you want the code to be uniquely decodable, it means that when I considered symbols from the nth extension of the source, then the code words generated based on the principle of nth extension of a block code should be non-singular. So, with this, let us define uniquely decodable non-singular block codes. So, a block code is said to be uniquely decodable if and only if the nth extension of the code is non-singular for every finite n. In the previous example, we saw that when we take the second extension of the block code, there are two code words which are same for two symbols from the second extension of the source. So, if this condition is not satisfied, then that non-singular block code cannot be uniquely decodable. Now, once if I have this definition, uniquely decodable codes, where the nth extension of the code will be non-singular for every finite n, what it implies that any two sequences of source symbols of the same length will lead to distinct sequences of code symbols. Now, this is not very difficult to see because it is by the definition of uniquely decodable. but we also desire that two sequences of source symbols of different lengths lead to different sequences of code symbols. Now, this is not very clear from this definition. So, let us try to prove this. Let us try to prove this by contradiction. So, let me assume that there are two sequences S1 and S2 which give rise to the same code word. Let us call that as x0. So, both these sequences S1 and S2, they could be of the same length or need not be of the same length, give rise to the code word x0. Let us assume that is same for both. Now, let us have another sequence which is S1 prime, and that is obtained by S2 followed by S1. And let us have another sequence S2 prime which is S1 followed by S2. Now, both these sequences are obviously of the same length, even if S2 and S1 are not of the same length. Now, the block code, if you assume that the codes are block code, then the sequence of code symbols corresponding to S1 prime would be nothing but x0, x0, and the sequence of code symbols corresponding to the sequence S2 prime would be again equal to x0, x0. Now, if we assume that our code is uniquely decodable, then what happens that for two different sequences I am getting the same code word. Now, this is in contradiction to our assumption that the code is uniquely decodable. For uniquely decodable codes, you cannot have two code words to be the same for the same length of source symbols. So, what it implies that if you have a uniquely decodable codes, then sequences of same length or either different lengths will give rise to sequences of code symbols which are different. Let us take an example of two uniquely decodable codes. So, let us look at the examples of uniquely decodable codes. Again, I consider that I have a source alphabet consisting of 4 symbols. I have my code alphabet which is binary, and I am interested in a binary uniquely decodable codes. So, let us say I have S1, S2, S3, S4, and let me have the code words as 00, 01, 10, 11. So, these are the code words for this symbols. Now, let me consider another code formed based on this code alphabet, which is given as 0, 10, 110 0. So, let me call this code as code A and let me call this code as code B. If you look at the code A, the code words have some unique properties. First of all the code words in this code are non-singular. Second, all the code words are of the same length. Now, if these two properties are satisfied, then so they are the same length and it is non-singular. If these two properties are satisfied, then it is sufficient to ensure that the code is uniquely decodable. Let us consider the code B. If we consider the code B, again it is non-singular. It is non-singular and it is a comma code. What I mean by that is that 0 acts as a comma to separate one code word from the next. So, this again implies that code B is uniquely decodable. From both this example, what it appears that the ability to tell when a code word immersed in a finite sequence of code symbols comes to an end can be seen to be central to the construction of both types of uniquely decodable codes discussed here. So, this property is at the heart of all uniquely decodable codes. Let us take another example of uniquely decodable code. Let us say that I have a code C where I have my code words given as 0, 0, 1, this code C is again non-singular and this is a uniquely decodable code, but there is a difference between this code and previous two codes A and B. The difference is that when I receive the sequence of code symbols, then I am unable to decode the sequence of code symbols code word by code word as it is received. For an example, let us say I have received some sequence of code symbols and I start scanning, and the first two symbols which I receive are 0, 1. Now, when I receive 0, 1, at that instant of time, at the time instant when I receive 1, I cannot decode it as S2. At that time of instance, I have to wait and find out what is the next code symbol. Because if the next code symbol is 1, 1, then what it means that it could be either now S3 or it is possible that it could be S4, because when I receive this symbol S3, now after this S3 if I receive 0, then I can say that 0 1 1 is S3, but if I receive 1, then I have to say that it is S4. So what it means that when I have this code, I cannot decode code word by code word as it is received. There is a time lag in the decoding process. I have to look forward to the succeeding code symbols before I take a decision to decode. So this is a distinction of the code C from code A and B. Though this is uniquely decodable, but there is a time lag in the decoding process. So what we say that this code is not instantaneous. So let us try to define what is an instantaneous code. So definition of an instantaneous code would be a uniquely decodable code is said to be instantaneous if it is possible to decode each code word in a sequence of code symbols without reference to succeeding code symbols. So in the light of this definition, code A and code B both are instantaneous, whereas code C is not instantaneous. Now it was very easy for us to find out whether a uniquely decodable code is instantaneous or not instantaneous in these three examples. But the question is it possible to find out or devise a general test for a code which tells when a code is instantaneous or not instantaneous? In order to do that, let us define something what is known as a prefix of a code. So let us define a prefix of a code. Let xi be a code word of some code that is xi consists of sequence xi1, xi2, xim chosen from the code alphabet X, the sequence of code symbols given by xi1, xi2 up to xij, where j is less than or equal to m, is called a prefix. Of the code word xi. Now, based on the definition of prefix of a code word xi, we define a test which will tell us whether code is instantaneous or not. So, that test may be stated formally as a necessary and sufficient condition for a code to be instantaneous is that no complete code word of the code be a prefix of some other code word. If this condition is, if this test is satisfied, then we can say that a code is a instantaneous, uniquely decodable, non-singular block code. Now, what it means here is, if you take the example which we had considered, if you look at this, you will find that the code C does not satisfy the prefix condition, because the code word corresponding to the symbol S1 forms a prefix to the code word of S2. Similarly, the code word S2 is a prefix of S3 and S3 is a prefix of S4. In fact, S1 is prefix of all the code words. Similarly, S2 is a prefix of S3, S4, and S3 is a prefix of S4. So, by definition, this is not a instantaneous code, because it does not satisfy the test of prefix. Now, we will try to see whether this test is really a necessary and sufficient condition for a code to be instantaneous in the next class.